Welcome everybody to the April APS meeting. This morning, or whatever time of day it is for all of you who are joining us, we're going to hear first from Dr. Gates and then Dr. Badger. So please, let's get this meeting started and welcome everyone.
Should I start?
Please do.
Deirdre, did you tell me to start?
Yes, please do. I think it'd be great.
Okay.
Oh wait, Dr. Gates might have just shown up.
I've been here, but with technical difficulties. I apologize.
It happens.
Shall I begin?
Yes, please. Thanks so much.
Good morning, everyone. I would like to welcome you to the April 2021 meeting of the American Physical Society. And our theme is Quarks to Cosmos. This session is the Kavli Foundation Keynote Plenary Nobel Prize session. We will have three fantastic speakers, recipients of the prize. Professor Andrea Ghez of the University of California, Los Angeles, Dr. Reinhard Genzel of the Max Planck Institute for Extraterrestrial Physics, and Roger Penrose of the University of Oxford. As you know, the title is Quarks to Cosmos. And of course, this is very appropriate at this time. I like to think of physics as the eternal chess game, namely humanity against nature. And just recently, nature has given us some hints of physics that we will be looking at in the future. There's the hint of the asymmetry in the decays of E mu and the G-2 experiments. And these precision experiments have excited the segment of our community in particle physics. And some of us have been waiting for this since 2006, when I spoke about the importance of precision measurements in particle physics. However, today, we will be recognizing the other part of our title, the cosmos. So this Nobel Prize recognizes discoveries in black holes. And last October, in our newsletter for the Physics Society, we wrote an article which was co-authored by Philip Buxbaum and myself. And my comment was, for science to advance requires unbounded leaps of imagination, but such leaps must be subject to rigorous observational examination. So we see two dichotomies, both illustrated in this Nobel Prize, with Penrose's work being the example of imagination, but harnessed to the power of mathematics, and the work of Genzel and Getz harnesses precision measurements with the exquisite use of equipment. So with that, I'm going to turn over the microphone to our CEO, Jonathan Bagger.
Yeah, so thank you, Jim. So I'm Jonathan Bagger, CEO of the American Physical Society, and I'm here today to welcome you to the 2021 April meeting, our second virtual April meeting. This year's meeting will have over 1,800 presentations. It's bringing together over 2,500 registered participants from more than 20 APS units and committees. And so I'd especially like to thank Deirdre Shoemaker and the program committee for making it possible. They have built an amazing program, one that reflects our global and inclusive community, and one that showcases the great diversity of physics in all its dimensions. From quarks to the cosmos, there are sessions at this meeting for everyone. I would like to recognize the many students attending this meeting, especially those who are making their first presentations. Welcome, and I hope you will stay engaged with APS for years to come, no matter where your future takes you. I'd like to highlight special session E22 on first results from the Fermilab Muon G-2 experiment, which will be held at 5:40 p.m. Central Time this evening. And I would also like to spotlight the Kavli Foundation Keynote Plenary, featuring this year's Nobel Prize winners, that will be held immediately following these welcoming remarks. On behalf of APS, I would like to thank the Kavli Foundation for making possible this exciting plenary session on black holes. I find it hard to believe that during my lifetime, they have progressed from science fiction to science fact. And even today, black holes still have much to teach us about gravity, quantum mechanics, and the evolution of the universe itself. So stay tuned. A few reminders. First, please adhere to the APS Code of Conduct. I ask that you conduct yourself towards others with the dignity and respect you would like to receive in return. Second, take advantage of the many virtual networking opportunities, including hallway encounters, unit events, and topical chats. Third, visit the exhibitors, the Graduate Student Fair, and the APS Village. And finally, enjoy the virtual experience. Virtual conferences are new to many of us, and also new to many in the conferencing world. So remember, we are conducting an experiment, one from which we hope to learn what works and what does not. We will have successes and failures, as you've already seen. So please be kind to each other and to the APS staff. Everyone is working to make this conference a success. And with that, let me close by saying how much I look forward to seeing you all next April in New York City. It will be terrific to be together again. It's my great pleasure to pass the microphone over to Dr. Deirdre Shoemaker, Program Chair of the April meeting, Professor of Physics at UT Austin, and former Chair of the APS Division of Gravitational Physics and of the APS Committee on Scientific Meetings. Deirdre, over to you.
Thank you. Thank you both, Dr. Bagger and Dr. Gates, for welcoming us all to the meeting this year. Little did we know a year ago that we'd be once again virtual, but I think it does open up the meeting to some people who might not have been able to make it. So welcome everyone. And I have to admit that when I heard who won the Nobel Prizes, I had a little happy dance because, of course, these are three people who have influenced so many of us in our careers. But I had a very interested about the black hole, both at the center of our galaxy and the theoretical foundations that these three people have formed over many decades with their knowledge. So I think I'm excited to introduce them, and I doubt we want to waste too much time before we get to hear them speak. But let me, again, with my program chair hat on, welcome you all and give a really big thank you to the APS staff personally, since without them, these meetings would definitely not happen. They're working behind the scenes even as we speak, making sure we have the best meeting we possibly could. So I know we're going to be about 2 minutes early. I'm hoping it's okay to start 2 minutes early because I don't really want to wait any longer to hear from our speakers today. And it is truly my honor to introduce them and to chair this session. So we're going to have the very first session today is going to be from Dr. Genzel, who's talking about the 40-year journey of what he's been studying. So let's see, without any further ado, let's hear from Dr. Genzel.
Okay, well, thank you very much, Deirdre, and dear colleagues. So I am the first here to go and discuss the progress we've altogether made in testing general relativity, and then also explore the issue of these bizarre objects, black holes, which were predicted by general relativity. And I'll be discussing with you one of the two experimental efforts which have gone into this. So I'm the European perspective, and Andrea will be the American one. Now, of course, this work as you might expect, experimentally is quite difficult. And so it has taken a long time, in my case, 40 years. So that's why I call this discussion a 40-year journey. It has also involved a lot of people. And I'm very grateful to all these many young and not so young physicists, astronomers, theorists, engineers who've helped make this a reality and improve the case now so much that we can be fairly sure that we've proven the existence of massive black holes beyond any reasonable doubt. Now, of course, all of this is on the background of a century of the theory of general relativity and black holes. And I want to just start by saying, let's recall that, you know, it was 1915 when the theory was presented to the public. Already 1 year later, Carl Schwarzschild found the first solution for a spherically symmetric mass. And that's when the event horizon and the idea of a singularity and black holes came about. And then it took, of course, you know, quite a while of, 50 years to improve on all the theoretical aspects. And I leave it to Roger to discuss the highlight of this work and just mention that, of course, actually the connection of the theory to the universe had to wait quite a long while until the first possible candidates became available, and those turned up in the 60s. First of all, the discovery of the quasars, very luminous radio objects, which were then shown by optical observers to be distant nuclei of galaxies emitting radiation at the factors 1,000 to 100,000 times greater than normal galaxy nuclei. And then, of course, also the compact binary X-ray sources, which we now believe to be stellar black holes. So that was sort of the first start when these two things came together, GR on the one hand, and the theory of black holes, and then actually going after them and finding candidates. Now, in the case of massive black holes, it's clear that what you would like to do to prove that they exist is not only to observe the phenomena like jets and X-ray and gamma ray radiation, but also to have substantial dynamical evidence from test particles, if you like, to really test out the gravitational potential and show that such black holes might indeed exist. Now, quasars are much too far away for this, that was clear. But Lindenbell and Rees in 1971 then proposed, well, if it is quasars are just galactic nuclei which happen to be in a state of very much increased accretion, so that they turn out to be active galactic nuclei, quasars. Maybe other galaxies, including our own, might also have such black holes, but not accreting very actively. So that really got, if you like, the observational studies going. And the Galactic Center turns out to be such a wonderful laboratory because it's so close. It's 27,000 light years only. And so here we can do things, measure things nowadays, as you will see, which you wouldn't have hoped, and clearly come very close to the central object. There's one disadvantage. The Galactic Center cannot be seen in the optical, and so intervening dust along the line of sight between the Milky Way center and us prevents optical observation. So you have to do this in the infrared, in the radio, X-rays, etc. But that in the end then led to what we know now, and which is what you will hear about now, and the evidence we have now from motions of gas and stars around the central compact radio source. Meanwhile, another pathway to black holes became available also only a few years ago, and also was recognized with a Nobel Prize, and that's gravitational waves, and showing that an inspiral-link double pair of such objects, in fact, then emitted very intense gravitational radiation until the merger of these two objects. And then finally, we have a third tool, which is to actually look at the centers of active galactic nuclei like quasars with radio waves, and look at the innermost regions, hot regions of the accretion zone, and where the jet is produced. And here in 2019, our colleagues produced the first 1 millimeter image of M87 and nearby AGN, and showed that indeed the light distribution is consistent with general relativity. So it's remarkable. Here we have 100 years, 50 years as far as the observations were concerned, were rather meager results, then slowly sort of empirically finding some objects, and then in the last 10 years, 20 years, we really had a breakthrough. So let me talk about the galactic center. I told you, you have to have long wavelength radiation. And so Charles Townes at Berkeley, for instance, was one of the first ones to enter the field because he knew how to build infrared equipment, infrared spectrometers. Here you see a picture of a modern adaptive optics picture of the central few light years of the Milky Way center in infrared light. So that is what Andrea and my group are doing on the big telescopes. And it just shows you that in the center of our Milky Way, there's a very dense star cluster. So these are nowadays our test particles. This is what we use to ask the question whether there is a central object here. Now, it turns out that in this central region, there's gas, in addition to a compact radio source, which I come to next. And these gas clouds were the first tracers one could use with Doppler spectroscopy in the infrared and also then in the far infrared and submillimeter region to look at the ionized gas, which you see here in pink colors, and the neutral gas, which is here in green. And it was Charles, as I said, Townes and others who looked at that and found those motions. At the same time, the radio observers started getting images of the galactic center at ever better resolution, including with intercontinental interferometry, and they found that there was a compact, extremely compact radio source at 1 millimeter wavelength, where the source is becoming somewhat optically thin. The size is a mere 40 microarc seconds. So that is about 4 times the mass, 4 times the radius of the event horizon of a massive black hole of a few million solar masses. And that indeed was indicated from the motions of the gas clouds that Townes and Lacey and Sarabin and others, and I then joined as a postdoctoral fellow in Berkeley in the 1980s, found. So on the left side, we were able to establish that whilst at large distances, the mass increases with radius, which is in the horizontal direction, within about 2 or 1 parsec, the mass then stays constant at a few million solar masses. And that is, if you like, the first dynamical evidence we had on the scales of a few light years, then that there might be a central object. Now, must it be a black hole? It's possibly a black hole, but surely not convincingly so. For one thing, many people felt that gas would be a poor tracer of gravity. You can jerk gas around with magnetic fields. You can push it around with stellar winds, which we know happen in this central region. So it's an uncertain tool, but actually it did, initially show us that on a scale of at least 1 million times the Schwarzschild radius, there seems to be a fairly concentrated mass. Now the rest, or the next of the part of the story, which undoubtedly Andrea will also talk about, is the fact that in order to get where we are now, we had to develop in many stages ever more sophisticated equipment to exploit infrared emission, to build imaging detectors. Then, of course, to correct the distorted wavefronts of the atmospheric refraction when the radiation from a distant object like the galactic center falls onto our detectors and thereby destroys the diffraction limited seeing. Instead, you have much poorer seeing dictated by the atmosphere. That is now overcome by adaptive optics on all the big telescopes. It was not so when we started, but it is now, and allows us to get exquisitely sharp diffraction limited images with the biggest telescopes we have. There's more. There's the integral field spectroscopy to do adaptive optics assisted imagery and spectroscopy over a finite field. And finally, in cases where you don't have a star to which is bright enough to correct the wavefronts, you send lasers into the upper atmosphere and generate a artificial resonant backscattering of sodium atoms, which looks like a star, which you can use to correct the atmosphere. So these technologies were coming in over time, and it took quite a while. The next thing is, of course, when you look at the stars and you want to use them as traces of the gravitational potential, you also need time to wait until things actually happen to change. And in fact, that was sort of the next stage of both groups. We working with the European Southern Observatory and Andrea working with the Keck telescopes. And then after a while, we did both hit our first successes, initially statistical measurements of velocities, but then the next big stage was to actually see accelerations. Andrea was that first, and then we both saw the first part of an orbit, which we actually couldn't have expected. That was really a gift of nature that nature gave to us, so that we can deduce from each individual star, in principle, the gravitational potential. And one such star is this star S2 or S02, which is on a highly elliptical orbit and approaches the central object, Sagittarius A star, to within only about 3-4 times the orbital radius of Neptune. And at that point, which it reached for the first time in May 2002, it has a velocity of about 2.5, 2.6% of the speed of light. That's incredible. And the velocity of 7,600 kilometers per second at that distance, if you calculate the mass from Newton, well, it's a few million solar masses. So it's the same mass which we had indicated from these gas motions on much larger scales, but now in a volume of only 17 light hours. So that's 1,000 Schwarzschild radii. So it's already a very strong piece of evidence that this might indeed be a black hole. Very difficult to think of any other configuration to fit into this small volume. Now, we both knew that the star S2 had a period of 16 years only, and therefore would be coming back in 2018. So at ESO, we had the situation that we could convince ESO that we might want to, when the star would come back in 2018, we might want to increase our measurement precision and resolution by combining the light from all 4 8-meter class telescopes on Paranal Mountain, which you see here in this picture. So that's called interferometry, like in radio interferometry. It's more difficult than in the radio, and I will spare you the suffering, if you like, and difficulty. But Frank Eisenhower with his team built gravity in this period of about 10 years, and we were ready for the incoming star when it came to its next showdown, if you like, in 2018. Now equipped with 3 milliarc second resolution and an astrometric precision of somewhere between 20 and 100 microarc seconds, so we can really pinpoint the orbit extremely well. So here you see the difference. On the left side, a beautiful adaptive optics image, but of course the center is very crowded with stars, and with interferometry, you can really resolve quite well near Peri S2, the star as it was coming in 18, from, in fact, the emission from Sagittarius A star itself, which I come back to later. And so then, during the Peri time in 2018, we were able to measure the spectra, but also the position so well that we could see the motion from night to night, which you see down in the center. SgrA star is there, the black circle above, and then the red points are the positions of S2 from night to night, and then Peri on May 19th, 2018. I should say that it's remarkable that, and highly unexpected, that we see such stars, because they cannot have slowly migrated into the center. So in fact, it's puzzling to see such stars so far in, but it turns out it's not rare. We have seen other stars. In fact, this year, right as we speak, another star, although fainter than S2, is coming in on an even deeper orbit. It has a ellipticity of 0.97, and it will reach Peri at 80 AU at the end of May. So that's still somewhat closer to the black hole than S2. So that's fantastic. It gives us an opportunity to, again, make valuable measurements and test, so to speak, the results we already obtained the last time. So what have we seen? Well, we've actually seen the first post-Newtonian effects of general relativity. Both groups have seen the gravitational redshift, which down below is in the residuals in velocity between the Newtonian orbit, which is at 0 there, the black line, and the data, which are the red data points there, and what GR would predict, which is the blue curve. So this is a very clear-cut confirmation of what GR would have predicted. The second effect we've also seen, which is the Schwarzschild precession. That, of course, as you may recall from the Mercury precession, was one of the first things which made Einstein's theory so famous. In the case of the highly elliptical orbit of S2, is a kink almost in the orbit, because the precession is the fastest near Peri. And you see this change in the slope of the orbit in right ascension on the left side, and then in angle on the right side. And then finally, as I said, SgrA star is active and accretes a little bit and energizes its accretion stream every 1 to 2 days. And then we see highly variable emission, and we were able on three occasions to see motions in this accreting material at the level of about 1/3 the speed of light, and at a radius of about 6 to 10 gravitational radii. So that's very near the innermost stable orbit of a 4 million solar mass black hole. Of course, we would go further. We would like to make this measurement of the spin. For that, we would need stars still further in, which I believe we can in principle do. The question is whether there will be any stars, and I'll come back to this at the end. Let me say that this innermost region in many ways is highly interesting because it's hot. The mean temperature is hundreds of billions of degrees, and the magnetic fields are likely very strong. And it turns out that the emission we see there from SgrA star, the variable emission, which you see on the left side in blue, varying over time scales of minutes, is highly polarized. And if you look at the U and Q Stokes parameters in red and green there, then you can see that they vary in phase. And that means that the polarization vector moves on the sky in a circle. And if you look at it, then the orbital, the period of this rotation of the polarization is with the period of the motion. And that requires that the fields are not toroidal, not in the plane of the motion of the orbiting hot spot, but probably poloidal. That, by the way, is something the event horizon community also have just announced to be true for the M87 black hole. From that, we conclude that there are very strong magnetic fields in this central region. I don't have time to go into this, but that's undoubtedly going to be more measurements and theoretical work in this general direction. So after 40 years, we've come from seeing the first indications of a massive object of a few million years, a few million solar masses at a few light years during Townsend's time in Berkeley, all the way now to the region right around the event horizon. And we are seeing always the same mass. The amount of extended mass within the S2 orbit is quite small. There probably are a number of stellar black holes and lower mass stars, but they're faint, and we hope to, of course, see them. Now, of course, the question is, must it be a black hole? And is it a single black hole? Well, the orbital, the Schwarzschild precession can be used to make a statement about any kind of a secondary object near the main black hole. And we believe that we can set a limit to about 1,000 solar masses for a second intermediate mass black hole near the big black hole. Now, there could be other intermediate mass black holes further out, but in central region, the black hole is by itself, if you like, and probably surrounded only by lower mass objects like stellar black holes. Let me finalize and say, must it be a black hole? Again, the same question. You know that the laudatio of the Nobel Committee for the work of Andreas and mine was not for the discovery of a massive black hole. No, it was for a supermassive object, because we have still not shown that the no-hair theorem is correct. And that's something which, of course, we would like to do. And so we have many plans with big telescopes, with interferometry. And then, of course, we all hope that maybe 15, 20 years from now, the gravitational wave work with LISA in space, if nothing else, will really put the crown on this by measuring the in-spiral of a stellar black hole into a massive black hole. Thank you very much.
And thank you very much for that. I'll do the applause. It's an awkward virtual applause around here. Thank you for your extremely timely presentation. So we have lots of time for questions. If people would like to ask questions, I'll start us by looking at our question and answer board. So we have one question from one of our listeners. And that question is, in the 1992 to 2018 video, you can see some stars having flickering halos. Is that something physical or just an effect from the telescopes?
That's from the telescope. I mean, the adaptive optics technology we are currently using corrects for about 30 to 40% of the total light. So you always have, an uncorrected fraction of somewhere around 50%. We will improve that in the next years, but that always leaves a certain amount of dirt. And so you have to post-process the AO images in order to, and so that leads to these dirt effects, yes.
Another question is, why are there no observations of S2 between May 4th and May 24th?
Well, that was just scheduling of the observatory. I mean, Desiree, as you could imagine, we are taking 4 telescopes. So these measurements, while in our opinion very beautiful, as seen by the other astronomers, means that they lose access to the VLT on all 4 telescopes for, say 4 or 5 nights. So it's a very expensive way of doing observations.
This looks like our readers will enjoy learning about some astronomy and how challenging it possibly can be. We have several more questions. If the objects that orbit the galactic black hole are confined to a plane, as in the case of stars in a spiraling galaxy, are the objects that orbit the galactic black hole confined to a plane?
That's a very, very good question. And the clear answer is no. Unfortunately, maybe Andrea has the image. I didn't have the time to show the image. So if you look at the distribution of orbital parameters of all these innermost stars, then they are, isotropic almost, and in fact, highly elliptical. They are even more elliptical than you would expect from a thermal distribution. And that may tell us something immediately about how they were moved in there. So the most likely process, most people feel, is the so-called Hills mechanism, where a binary of stars is basically by random chance shot on a near lost cone orbit, and is then, as it comes into the center, sort of separated in a 3-body interaction between the big black hole and the 2 black holes. And when that happens, then this extremely radial orbit of the binary relieves a captured star with a very high ellipticity.
Cool. Thank you. So what is the magnitude of the perihelion shift?
Of the what?
The perihelion shift.
Oh, well, the gravitational redshift.
I guess so, yeah.
Yeah, okay. Well, the gravitational redshift parameter is 2 parts, actually. One is just special relativity, and the other one is general relativity. And together, they are 200 kilometers per second for S2. And they're, in fact, a little bigger for the incoming star, which I mentioned. I mean, the star, S29 has an even stronger gravitational redshift. And of course, in the end, if we are lucky eventually to get a star deep in the potential, which is really in there, then we might see the lens steering precession, which of course then gives us a spin.
That would be really cool. Another question is, what are some of the constraints from this observation on quantum gravity theories?
Oh my God, I wouldn't dare. I wouldn't dare. No, we don't. No,
sorry,
we
I'm
don't.
not filtering the questions.
Yeah,
I'm just
at a
reading.
mundane level, I would say, still, as I said, of dreaming that, at least for me, as in my lifetime, to perhaps see the spin measurement and perhaps do a no hair test. I mean, that really is, because, for anything having to do with quantum effects of the black hole, you really would have to make precision measurements at the innermost stable orbit or the photon orbit, okay, and even then, I'm not sure we would know what we should expect as deviations.
It would be really exciting, but I'm with you. I would love to hear about that spin, but short of sending a probe inside the black hole, I guess we're gonna have to wait. Okay, if Charlie Towns were still with us, what recent finding do you think he'd be most excited about? Kind of.
Oh, I think, for Towns, you have to see, you wouldn't believe that now, but we wrote, Towns and the Berkeley team wrote a paper in '85 to Nature, not a letter, but a big Nature article where we announced that this is a black hole. And Towns was always convinced. And every time Andrea and I came up with the later results, he would say, oh, that's great, that's wonderful. But you see, I knew about all of this already in 1980. No, that's I mean, great. Towns clearly was delighted to see the progress. And in fact, also in the sense that the 2 teams finding most of the time the same thing, which made, of course, acceptance of our results more easy.
Are there any prospects of measuring deviations in gravitation from higher curvature effects?
Well, okay. I mean that requires to go up in the post-Newtonian terms of course, and we've made mock tests of what we would need to see these tests, and for this we would need a star which is at, say, a third or a half to a third of the Perry of S2. And so, I mean, my delight is to, what I've told you today is we are seeing stars which are coming closer than S2, but we have not yet seen a star which is half or a third of S2. And of course, this could be a very faint star, but then the Hill's mechanism actually favors for the closest captures the more massive stars. So it's not clear to me what we could use. Stellar black holes we can't see. So that's unfortunately that's the ultimate weapon, if you like, to use the stellar black holes.
Mm-hmm. Does your work show any residual evidence of prior galactic mergers?
Prior galactic mergers? I don't think so. I don't know. Not in this innermost region. I mean, of course, the one of the questions which is sort of astrophysical nature is the fact that the naive, if you like, standard prediction is if you have a massive black hole, then you shouldn't see many young stars around it, because basically gravitational collapse of normal interstellar gas clouds are prevented by the tidal disruption, tidal stretches of the black hole. Yet the galactic center is the central nuclear cluster is one of the most active star forming regions in the Milky Way. So that's a strange thing by itself. Andrea has called it the paradox of youth. Okay, and basically what we have learned is that it's possible for, say, a gas cloud to come in. That could be triggered by a merger, of course, but doesn't have to be. It could just be a gas cloud which came in and then was chocked and then over time collapsed and formed stars.
The earlier question on the shift was actually, they're wondering what is the para-astra shift? Do you actually have a measurement of how much, the angle which the para-astra shifts due to the precession?
Yeah, that's 11.9 arc minutes of what I call the Schwarzschild precession. Okay, which, as I said, in the case of such an elliptical orbit, is not a sort of a slow drifting of the phase of the orbit. It's basically most of the change in angle happens within a year of Perry, and then basically the orbit doesn't precess as it goes further out.
Someone asked, is there any dust or perhaps gas between the innermost star and the black hole that could be affecting the measurements of mass?
Yeah, there is hot gas, which we see obviously in the case of the synchrotron emission, but the density of that gas is very, very low. And in fact, from the very fact that as I mentioned, that the magnetic field structure of the innermost accretion zone seems to be non-toroidal, that gives you a quantitative statement that the magnetic pressure, which we think we know, roughly speaking, must be larger than the gas pressure. And that gives you immediately another statement about the amount of gas which there is. So no, the star S2 is like a bullet, which is going through a thin medium of gas, which it doesn't really see.
Now, we still have a couple minutes if you still have the patience to answer so many questions. There's several questions in the chat about the possibility of measuring higher post-Newtonian effects in the near future. Is that something that's possible?
Yeah, no, I think as I mentioned several times now, it's just a question of getting the right star. And in a way, you could say after S2, we had sort of a shall we say, post-birth depression, because we knew from the orbits of the stars which we knew about that it would take another 5 or 10 years until the next big star would come in. But luckily enough, he is 1-2 years later coming. So as we are more capable with interferometry and the big telescope, the next class of 30-meter class telescopes, to go fainter and more precise, we can hopefully then go into this innermost region, which is otherwise very confused with 8-meter imagery.
Mm-hmm. So one of our listeners asked, would an orbiting pulsar provide those higher order post-Newtonian terms?
Of
We got
course,
lucky to have a pulsar.
of course, of course it would, and it's very clear that if we would be lucky that a neutron, obviously there should be many neutron stars, and so that was a hope early on, and even when I was a student at the 100-meter telescope in Bonn, they were looking then for pulsars in the galactic center. That would have been fantastic. A pulsar has now been found, but it's a magnetar. It's a extremely high magnetic field object which can not be used as a clock, and no other normal pulsar has so far been seen. But people are looking hard. I mean, it's possible. Sure, there should be many neutron stars.
Wonderful, thank you. I think it's time to get ready for our next speaker.
Okay,
so let's
you.
Have a warm thank you again. That was a lovely talk, very interesting to hear about all and future looking, what we can look forward to in the future.